Hello everybody, it's Mrs. Pound and I'm back with another video for Chapter 3 on measurements in chemistry. This is from BJU Chemistry 5th edition. So our topic for today is from section 3.2. It's the second video in this series and it's about significant figures. Now, this is probably one of the first times you've ever heard about this, so I'm assuming that this is a pretty new topic for all of you. So our objective today is going to be to explain the role of significant figures in measurement. So what is a significant figure? It is the digits in a measurement that include those that are known with certainty plus one estimated digit. These have to really do with the precision of measurements, how precise we can get, how exact, how close to perfect we can get our measurement. Now, our measurements will never be perfect or exact. Because we just can't measure that fine. I mean, there's always some uncertainty in measurement. So this shows us what that uncertainty is. So significant figure rule number one is that significant figures apply only to measured data. Significant figures do not apply to counted or pure numbers. For example, 500, if we count exactly 500 pennies or 500 of something, it doesn't apply. One pair, the square root of 3 or pi, okay? It does not apply to these types of numbers. Significant figures do not apply to conversion factors either, okay? Because these are exact quantities, so it does not apply when we talk about our rules. Significant figure rule number two is that all non-zero digits are significant figures. So if in a number, the number is not zero, it counts as a significant figure. So for example, 25.4 milliliters, that has three significant figures because it has three non-zero numbers. Over here, 13.778 grams, four significant figures because there are four non-zero numbers. So that's pretty straightforward. So if a number is not zero, it is significant. Significant figure rule number three. All zeros between non-zero digits are significant figures. So in 100.5 degrees Celsius, because these zeros are in between non-zero numbers, they count. So there's 1, 2, 3, 4 significant figures in this number. In 1.09 grams, there are three significant figures because the zero here counts and always non-zero numbers count. So 1, 2, 3. Significant figure rule number four. All ending zeros to the right of the decimal point are significant figures. So for example, 20.0 seconds has three significant figures because this zero, because it's after a decimal, is significant, and this zero is significant because it's in between two significant figures. So we have 1, 2, 3 significant figures. And 250.00 liters, there are five significant figures because these are after the decimal, and this is in between two significant figures. So all of those are significant for 5. However, in 0.075 kilograms, there are only two significant figures. These zeros are not significant because they are placeholders. I do realize that this one is after the decimal point, but it's not significant because it's acting as a placeholder. We're going to learn later for less ambiguity, we can write these as scientific notation. And if we rewrote this in scientific notation, it would be 7.5 times 10 to the negative 2. And so then we would be able to clearly see that there are only two significant figures. But place holding zeros don't count. Also, 0.0010 seconds. This one counts because it happens after another significant figure, after a decimal. But these 3 zeros do not count because they are simply placeholders. So this number has two significant figures. Now, let's talk about something that can be a bit ambiguous. It is difficult to determine the number of significant figures for a number like 2,500 milliliters. To eliminate confusion, use scientific notation. Now, if I had a decimal point at the end of this, I would definitely know that it's four significant figures because a decimal point would indicate that this zero definitely counts. But to eliminate confusion, like I talked about with those other place-holding zeros, we can use scientific notation. So if we wrote 2,500 as 2.5 times 10 to the third milliliters, we would clearly see that there are two significant figures here, the 2 and the 5. If it was written as 2.50 times 10 to the third milliliters, we would see that there are clearly three significant figures. This would count because it is after the decimal, so 2.50. Three significant figures. And if it's written as 2.500 times 10 to the third milliliters, we would see that there are clearly four significant figures. Okay, so I hope this, when we're talking about significant figures, I hope this also emphasizes with you why we write measurements the way we do, why I always insist in lab that you make certain measurements to the 10th place. You make them to a certain place and don't drop zeros or don't drop that place when you're making the measurement because it's significant. It's estimated or it is a number that you have actually read. This is really important in our measurements for really credibility reasons, okay, to make our measurements very credible. So don't drop those significant figures. So our objective today was to explain the role of significant figures in measurement. Don't forget your 5 questions, and I'll be back with another video about how we use significant figures in our math calculations.